for the dividing polynomials, the remainder and factor theorem. In this second part, we're going to start with the remainder theorem and how we can apply the remainder theorem to find the remainder of a polynomial division problem. Now, the remainder theorem states that if a polynomial function f of x is divided by a factor, or divided by a value of x minus some constant right there, then the remainder of this division is going to be equivalent to the value of our function at the opposite of that constant. So what this means is you can divide and determine specifically the remainder by simply substituting in the opposite value of c of the constant into the dividend. So let's look at an example of this. Let's jump straight into example A here. So here, if the question is to determine simply the remainder, what's the remainder of this thing, without having to use long division or synthetic division, I can determine the remainder by simply plugging in the number 5, the opposite of a negative 5, positive 5, into our x and evaluating that. And while using any type of calculator, handy dandy calculator right here, we end up with a total of negative 4,887. So this is going to be your remainder. So for this example, if our objective again is to simply find the remainder, not to actually divide this, and only focus on what the remainder is, we can get that according to the remainder theorem by simply plugging in the opposite of this value, so positive 2, into our expression. And this equals to a total of 25. So that is our remainder for our second example. Now let's look at an application of this concept in a real world setting. So we have here the concentration of a medication in a patient's bloodstream in milligrams per liter, mg over liters, is modeled by this polynomial c of t equals negative 0.1 t to the third power plus 0.5 t to the second plus 1.2 t plus 5, where t is going to be the number of hours after the medication was administered. Now, if the concentration of this medication is decreasing by t minus 4, milligrams of liters per hour, how much of this medication is going to be left in this bloodstream? Okay, so let's see. Let's see how much medication is going to be left. So right here, we would have to take away this amount until we have again, and we depleted the amount, and all we have left is a remainder. Well, subtracting an equivalent amount every single time is the equivalency of dividing. So if I divide this by this, I should end up again with a remainder, and that's how much of this medication is going to be left over. Well, according to the remainder theorem, I can get that value by simply plugging in the opposite of this number into my function. So I'm going to evaluate c of 4. So by substituting in positive 4 into this function, I can evaluate and determine how much is going to be left if the medication is decreasing at a constant rate. So taking that amount throughout the entire time. And evaluating this is going to end up with a total of 11.4. So that's the amount, milligrams per liter. So this is the amount of medication left in this patient's bloodstream. Let's now look at a different application of this idea. So here we have that the amount of fuel in a rocket's first stage booster is modeled by this polynomial function f of t, where f is the fuel in thousands of gallons and t is the time in seconds after liftoff. Now, how much fuel is left after the first stage booster if the rocket uses t minus 10,000 of gallons of fuel per second? So let's see how much is going to be left again if this is the amount that is decreasing. So if it's decreasing by this amount, then we taking away this amount every single second until there's nothing left over, until we deplete everything will give us the remainder, which is the result, again, like I mentioned earlier, of dividing. So using, again, the remainder theorem to figure out how much is going to be left over, the remaining amount, I can substitute in the opposite of this value into our function of f. So plugging in 10 will give us negative 2 times 10 to the third power minus 10 minus 30 times 10 to the second minus 10 times 10, and then plus 4,000, which equals to a grand total of negative 1,000. So this is going to be an issue again for these aerospace engineers, because the model that they have right here wouldn't have enough, because it's using way too much gasoline in that first. It's not going to have enough even to finish that first stage of booster. And hence why, again, creating these models is important, again, in applications, to be able to correctly have, in this case, the right amount of fuel to get out of this first stage of booster. So here you see we have a negative value, so it's not going to have enough fuel to get out of the first stage booster protocol. But like I said, that's your remainder. Now the next theorem I'm going to discuss is the factor theorem. The factor theorem states that if f of x is a polynomial, then x minus c is a factor of this polynomial if and only if, using the remainder theorem and plugging in the opposite of this value here, gives us the value of 0. So if our remainder is equal to 0, then this is going to be a factor, and vice versa. If x of c is a factor, then the remainder has to be 0. So I can easily check, using the remainder theorem, if something is going to be a factor or not by using, again, substitution and plugging in the opposite of these values into my function. And if the answer is 0, then that would imply that this binomial is a factor of this polynomial that will divide it with no remainder left over. So let's check that example. So let's check right here. Let's determine which of these binomials is a factor to this function. So we're going to evaluate f at positive 3, evaluate f at positive 1, evaluate f at positive 4, and evaluate f at positive 2. So using our calculator, I'm simply going to replace all of these x's first with the number 3, and let's see what that gives us. If I plug in the number 3, that equals to 0. Now I'm going to do the exact same thing and plug in the number 1. Again, positive 1 into these x's. And again, using the calculator, just to be quick, that's going to give us a value of 16. When I plug in the number 4, that's going to give us a total of 22. And when I plug in the number 2, I also get 0 again. So of these binomials, the factors are going to be x minus 3, and x minus 2. So those are the two factors to this expression right here. Let's do a look at the second example. So for this example, let's determine which of these 4 is going to be a factor. So we'll do the exact same thing and evaluate f at positive 1, since this is minus 1. Evaluate f at negative 2, at negative 1, and at positive 2. Now for practical purposes, I'm just going to simply plug them into my calculator. And 1 to the third power minus 8 times 1 to the second minus 11 times 1 plus 18, that's a total of 0. When I plug in negative 2, that also gives me a value of 0. But when I plug in negative 1 and positive 2, I don't get 0. I get 20 and negative 28. So that means by this factor theorem, that implies that this and this one are going to be factors to f of x. So we have 2 of the 3. And again, from the linear factorization theorem, I know that there would have to be 3 factors, because again, it's x to the third power. So I can break this up into the product of three linear factors. X minus 1, X plus 2, and then X plus or minus some other constant right here, okay? But here are the two of the three factors. Now let's apply this concept to a real world scenario. So in the example C, we have that the engineer is designing a roller coaster track. Now the path of a section of the track is modeled by this polynomial function h of t, where h is the height and t is the time in seconds. Now the ride needs to have support at points where the track is going to reach the ground level. So that means that the height is going to equal to 0. So at which of the following time intervals does the roller coaster need supports? So using the factorization theorem, we want to know when this is going to equal to 0. So we're trying to figure out at which input values using our factorization theorem do we get a value of 0. So in other words, at which one of these which one of these four, which ones are going to be factors of h? Not f, there should be h here. Let me erase this because the function is h. So h, 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 and h. So plugging into the t values of h, we're going to get 0. Plugging in negative 1, I'm sorry, positive 1, that should be positive 1 because it's the opposite of that number. That's also going to give us 0. When we plug in 4, that gives us 6. And when we plug in 3, that gives us 0. So by the factor theorem, that means that these three are going to be factors to this function, which is exactly where the height is going to be 0. And let's look at the last example. I have a programmer is creating a simulation, and an important calculation in the code is represented by this polynomial. Now the simulation will crash if the function is 0. So if this thing is equal to 0. So which of the following binomials will the simulation crash? Which is equivalency you're trying to determine, since we're trying to see what makes f of n equal to 0, is a factor. So in other words, which of these are going to be factors to this function f? So using the factor form, the factor theorem, all I have to do is evaluate f at negative 3. And I see at negative 3 I get a value of 12. So that's not going to be a factor. So that means that's not where the where the simulation is going to crash. If I evaluate f at the opposite of positive 4, negative 4, that gives me 14. So the simulation will not crash. The value of f at negative 1, that's negative 16. So the simulation won't crash. And at negative 2, that does equal to 0. So this is a factor. N plus 2 is a factor to f of n, which means that it makes it equal to 0. And that's going to be the place where the function is going to crash as a result. So we only have one possible place here. Okay, well that concludes our second part of our examples for this 5.4. I hope again it was helpful. If you have any questions, again, contact me through Parent Square or through email. And like always, I appreciate you watching and I hope you have a great day. Goodbye.